All right, thank you for that very flattering introduction. And yeah, I only ever hear people call me Dr. Lennox when I'm sort of visiting or doing seminars, so that's always interesting too.
Yeah.
A little bit of background about me. I grew up in Texas, from Plano, which is near Dallas. I got my PhD in statistics from Texas A&M, as you know. But what you don't know yet is that I also got my bachelor's degree in applied mathematics from Texas A&M, and I got a master's degree in statistics from Texas A&M. So I'm as Aggie as you can be. Assuming you're not in one of the newer buildings, I have probably literally sat where you're sitting right now. If you're in Blocker, I definitely have. So interesting sort of progression in terms of my academic career. I got my applied math degree and decided to go for the master's in statistics. I was not originally planning to go for a PhD. I was sort of talked into that while I was a member of the department. So I can give you some insight maybe into why I decided to make that decision. If you're curious, I was originally planning to go into academia. And so I'd written a series of papers. I was interviewing at a bunch of universities. And then my life took a very different turn after I had my sort of throwaway practice interview at the joint statistics meetings in 2009, where I was part of the, I don't remember what it's called, but sort of the job search program that they run at the big conference. And I decided that I would do an interview with a place called Lawrence Livermore National Laboratory in Livermore, California, thinking that I would never ever work there because I didn't know anybody in California. And if you grow up in Texas, then all you really know about California is that it's really, really expensive.
Yeah.
So it was my first interview at the conference, and I walked out of that interview thinking, well, you know, I'm going to have to change my plans because apparently there's a good chance I'm moving to California after all. And that led to my getting a postdoctoral research position at Lawrence Livermore in bioinformatics, which was what I had focused on during my PhD. And then after I stayed there a little while, I shifted out of bioinformatics and more into the I don't want to say the harder sciences because biology is a perfectly hard science, but I moved more into engineering, more to work with physics. I have a series of papers I can talk to you about that involve things like how do you use statistics and data science to do a better job working with large-scale computer simulations. So something Alan didn't mention about national laboratories is that they are typically the home of the highest performance computing hardware in this country. So for example, Lawrence Livermore had the fastest computer in the world for a little while called Sequoia. You get to have the fastest computer in the world for about 6 months usually on average, and then Oak Ridge had it, and I believe it's currently in China. I can talk a little bit about error analysis for micro CT applications. CT is computed tomography. It's the same thing that you would have in a hospital, for example. It's an imaging technique, so you get sort of a 3D picture of the inside of something. It's also used in industrial applications, and so I did a little bit of work on that at the laboratory. One of my last projects before I left was in neutron detection. And neutron detection is a very important sort of subset of radiation detection, which is of interest for things like understanding how nuclear power plants are working or how sort of nuclear science experiments are working. It's also very important for nuclear non-proliferation. So basically making sure that people are using a power plant for good things instead of using a power plant to sort of make precursors to nuclear weapons. While I was at Lawrence Livermore, I also founded, with the help of Paul Kidwell, my boss at the time, the Statistical Consulting Service for the laboratory, which was actually modeled on the graduate student Statistical Consulting Service at Texas A&M. And the premise behind it was that it can be really hard to get people to talk to a statistician if they have to bring money to the conversation. And at the laboratory, we billed our hours kind of like lawyers. So people would be reluctant maybe to approach a statistician if they knew that they were going to have to pay them from the first conversation. So we said, okay, we're going to give you a limited amount of statistical consultation and statistical advice for free. And maybe that's enough if you have a simple problem, or maybe it convinces you that no, you really do need to include a statistician on your project or write a statistician into your next project. Something else that I did while I was at Livermore, I was a project manager for a few years. If you have any questions about what that's like. As part of my role as the head of the Statistical Consulting Service, I also did a series of talks that ended up on YouTube, which was a very interesting experience. And I became, the statistics lady at the lab. That was a lot of people recognize me who I didn't know personally. And what else about the laboratory? It was a absolutely fantastic job. I can't imagine a better first job out of school than the lab. And not just Livermore, although obviously I'm biased in its favor, but Los Alamos, which I believe is where Dr. Dabney worked, the Office of Science Labs, places like Oak Ridge or Argonne or Lawrence Berkeley, all really incredible places to do science and engineering. And as a statistician, to interact with really, really smart people on really hard problems, and to see the power that your statistical training gives you and the ability it gives you to contribute. Because a lot of times I was not, the smartest person in the room or even the best person at math in the room, but because of the way statistics gets you to think about science and engineering problems, I still had something to contribute, and I was able to help to push things forward.
Yeah.
So anyway, I had this absolutely fantastic job. And then in I want to say it was late November of last year, got an offer I really couldn't refuse from GE Aviation. And I stopped being a statistician. I sold out and I became a principal data scientist. So if you're curious, I can't tell you a whole lot about GE Aviation because I'm still brand new. I've been there, I think it's 3 months this week. But I can tell you what that sort of career change process was like. I can also maybe give you a little insight into what does data scientist mean versus statistician, because I was actually pretty surprised. People were saying, oh, yes, we want like a data science expert and someone who knows all about artificial intelligence and that kind of thing, when really we're looking for somebody just like me. I mean, I haven't changed my LinkedIn profile. My qualifications are exactly what they were. But it turns out a lot of times when people say they want a data scientist, they really are looking for someone with a lot of statistical training.
Okay.
So that's me. And I guess any questions really about anything. It could be about national labs, about my career path, about why go to grad school, that kind of thing.
Yeah, I do think one good question I definitely want to be asked, so I'll go ahead and ask it. What are the national laboratories? What roles do they play? Who runs them? What kind of work do they do? What other kinds of general characteristics can you share?
That is an excellent question, and I'm glad that you asked it. So the National Laboratory System is run out of the U.S. Department of Energy, and it actually has sort of two pieces. And you might say, why does the Department of Energy run the National Laboratory System? And it all dates back to the Manhattan Project during World War II, which was when the atomic bomb was developed at Los Alamos National Laboratory. And so that is how the national laboratories started. It's not all of what they do today. There are laboratories that are called NNSA laboratories, which are National Nuclear Security Administration. And those are Los Alamos, Lawrence Livermore, and Sandia. So you can sort of think of Los Alamos and Livermore as being sister laboratories called the physics laboratories. And during the Cold War, they actually had a role in the development of the nuclear stockpile. We are no longer building new nuclear weapons in this country. We are no longer testing nuclear weapons in this country. So what those laboratories do now is they basically ensure that the stockpile is still safe and reliable without doing any testing. And that's called stockpile stewardship. And that's not all they do. That's, I want to say, maybe a third of the laboratory's budget. In Lawrence Livermore's case, it's actually an outstanding center for excellence in laser science. So we have the largest, most energetic laser array in the world. It's called the National Ignition Facility. It was featured as the warp core in the second of the Star Trek reboot movies, so you might have actually seen it. And what the NIF is intended to do is basically replicate conditions of exceptionally high pressure that can't be produced anywhere else on Earth. And it does have a role in the stockpile stewardship mission, but they've also used it to study what the interior of giant planets is like. So for a while, they were using it to say, what's it like on the inside of Jupiter? They're using it to discover new phases of matter that you can generate at those exceptionally high materials. And it also has a potential role in clean energy, because you can generate nuclear fusion in the NIF target chamber, which basically means you're squeezing hydrogen atoms so hard that they fuse into helium and they release energy at that time. And this is a potential alternative source of energy to the fission reactors we use today. And it would hopefully be much cleaner. You don't have to work with materials like uranium. It works off of, basically water. And yeah, so there's a lot of potential there for new energy source. And they're still working out, exactly how to do it. But that's one of the reasons that they built the NIF. So those are the NNSA laboratories. There's another set of laboratories which are called the Office of Science Laboratories, and those are not directly tied to the nuclear stockpile mission. They do sort of more generalized big science kinds of projects. So for example, I'm trying to remember its name, but there's a lot of particle accelerators in the United States are run through the Office of Science. A lot of computing research happens through the Office of Science. So I mentioned that Lawrence Livermore at one time had the fastest computer in the world, and then it was supplanted by a computer that's at Oak Ridge. Oak Ridge is an Office of Science laboratory. Lawrence Berkeley, which is sort of our neighbor up the highway, is an Office of Science laboratory. And they do all kinds of different scientific research. There's a lot of work in biology. Actually, Lawrence Livermore played a role in the Human Genome Project, although more of that happens at Office of Science laboratories now. A lot of basic physics, a lot of basic material science, for example. How do you build a better battery, which is a huge deal, if not just in terms of our handy electronic devices that we carry with us, but in terms of alternative energy. So one of the reasons that we can't scale up wind and solar power is because they're intermittent. So the sun doesn't shine all the time, the wind doesn't blow all the time. If we could store energy efficiently from when those things were happening, that would mean that we could use more of these sort of renewable resources as opposed to the non-renewable resources that have to provide this baseline power for the grid right now. So yeah, the official motto of Lawrence Livermore is science in the national interest. Yeah, it's a really incredible place to work. Any national laboratory, frankly, is a really incredible place to work.
Cool. All right. Well, let me just recap the high points of your basics real quick, and then ask students what questions they have. So, Texan, Aggie, got a PhD, was not predestined to have this path that she wound up in. She kind of followed her path and found an interesting job. Now she has another interesting job, and done intellectually stimulating and fulfilling and impactful things along the way. So the folks in the room are undergraduate majors, and who knows where they're going to end up, whether we're going to go to graduate school or not, what kind of jobs and careers we want to go into. So your turn. What kinds of questions do you have for Dr. Lennox? Go ahead, Kurt.
Do all these projects, are they all assigned from above you, or at any time can you work on some sort of project that you're interested in specifically for yourself?
So I kind of heard that, but Alan, could you repeat it?
In your experience, there's projects that you're part of a team that's kind of being collectively directed at one problem. Kirk was asking, does it happen that you get to work on things of your own choosing, like your own projects? Can you pursue your own kind of pet projects in the places that you've been?
Yeah, so that's a great question. But before I answer, there was something that I meant to say in my intro that I forgot. I promised my previous and current employer that I would mention as part of this, since it's being recorded. I speak only for myself. I don't speak for Lawrence Livermore or GE. You're just hearing my personal opinions.
Gotcha.
But that being said, can you work on sort of your own projects? Yes, you can. It's the extent to which you are self-directed varies a lot depending on where you work. So my impression was that probably academic statisticians are the most self-directed, particularly if they're not in what are called soft money positions. Soft money means more of your salary is paid from grants than say from just by a university. it's always about, can you get somebody to give you money to do what you want to do, basically. At a national laboratory, like I said, Lawrence Livermore is about science in the national interest. We're also fairly expensive, and we are not allowed to compete with private industry. I say we, even though I'm not there anymore. I was there for a long time. However, within certain legal constraints, like the one where you can't supplant private industry because it's considered unfair, because it's a government-funded institution. Yeah, you have a lot of freedom to do the kinds of things you want to do. You can't pick absolutely anything, but you can write proposals and apply for grants. And some of these are internal grants at Lawrence Livermore to do the kinds of things that you want to do and that you think are important, as long as they're aligned with the lab's mission. And I hope you got the impression from my sort of discussion of national laboratories. There's a lot of stuff that falls within the basis of the laboratory's mission. I'll give you an example. One of the last projects that I was working on at the lab was it was basically building a better neutron detector. And this was the dream project of the gentleman who was the original principal investigator for that. And so he went through a process where he got internal support at the laboratory. He got connected with people at a federal agency that had grants available, and he wrote a proposal, and he got the funding for his dream project. Admittedly, it had to be aligned with the laboratory's mission, and it was. And he didn't get it on his first try, but it was still pretty flexible. I tended not to write grants. I did a few times. What I tended to do was just look around and see what projects other people had gotten funded, and then pick the ones I really wanted to work on. So for example, I really wanted to work with this guy in the neutron detection project, so I made time for him. There's certainly, after my like initial year at the lab, when I didn't know anybody, it was a lot of my projects came through the network, and no one ever came to me and said, you know, Kristin, thou shalt work on project A, even though you're not that interested in it. It was sort of, I was expected to keep myself busy. And if I ever hadn't had enough projects, yeah, somebody would have come in and said, okay, well, you know, you're going to work on that because you have to fill up your time. But frankly, the laboratory has, I want to say something like 5,000 people and something like 10 statisticians. So there was always more projects than there were people with statistical training to work on them. So we had a lot of flexibility in terms of what we wanted to do. GE is different because GE, you know, it has a mandate to make money. It's also an absolutely huge institution. I mean, I think GE Aviation is about 50,000 people. GE overall is about 300,000 people. And so there is more of a hierarchy feel to this job, where, you know, you just have to have more centralized control to get 50,000 people all working towards the same thing. That said, you know, I have a colleague who just submitted a proposal to our boss and, you know, got approval to do a proof of concept for something new. So it's a spectrum in terms of how much flexibility you have in terms of what you work on. It's also a trade-off in terms of how big an impact you feel like your work is having. Like when I was doing my academic work as a graduate student, you know, I was writing papers, and they were good papers, but I felt like not many people were reading them. Whereas, you know, first at the laboratory, I knew I was working on big things that mattered. At GE, I mean, it's a phenomenal company. There are not that many places that make jet engines, which, by the way, is what GE Aviation does, in case you didn't know that. And yeah, so it's you sacrifice a little bit of flexibility, but in exchange, you get to be part of something huge and very impactful. So that's kind of how I see it.
Cool. Who else had their hand up? Andrew? Okay, go ahead, Andrew.
So I'm currently planning to pursue a double major in applied mathematics and statistics, and I'm actually kind of also hoping to be a data scientist, kind of. I was wondering if your background in applied mathematics helped you or hindered you in any way in your your further education in other ways. Like, did it help in any way? Or is any advice potentially? Yeah,
so he was asking, he's considering APMS and stat double major, and soliciting your input on what's the role of applied math and what's it going to do for them, I guess, and what.
Like how has it helped?
It will
How
do
has
an
it helped?
enormous amount. Yeah, it's huge. So my bachelor's was through the applied math program. So again, slightly biased.
Mm-hmm.
The first thing I will tell you about being a statistician in the wild is that very, very few people know what statistics actually is. They will look at you as sort of a mathy person. So if they have a mathy problem, they will bring it to you, even if it had absolutely nothing to do with statistics. I have been asked questions that are straight up optimization questions. I have been asked computer science questions. I have been asked operations research questions. And in a lot of cases, sometimes I couldn't solve them. I said, you really need to talk to the operations research group. But it was the background I had in sort of broader math that let me understand what they were talking about and who to talk to. And in a number of cases, if it was a fairly simple thing, I went ahead and did it myself. So for example, I've done discrete event simulation, which is straight out of operations research, not really something we talk about a lot in statistics. It's not that hard to do. And it was a math background that let me do that. Mm-hmm. I've done optimization. I've done work with machine learning concepts that really aren't statistical concepts. Like one of my papers is sort of a customized version of a support vector machine. And the reason I was able to do that was that I was a mathematician before I was a statistician. So I'm deep in statistics, but I'm broad in math. The other thing that I really like about the applied math program at A&M is that they promote a lot of computer science, even if you're not taking the version that has an emphasis in computer science. And when I was an undergraduate, I got up through, what was it? It was data structures and algorithms. I think that was a 300 level course at the time. And I have never regretted any of the computer science classes I took. Like I studied 3 different programming languages at A&M. I've learned many more since then. Especially if you're working in the part of the world where I'm working, so sort of this Silicon Valley nexus, computer programming is something that's just sort of expected. Mm-hmm. It's something that a lot of people know how to do, and you need to know how to do if you're going to work in this area, and beyond just something like R or SAS. Okay. So I think that was, I've derived enormous benefit from having the broad math background, and I'm all for it. Statistics is best, but math is wonderful.
Okay. Taylor?
Yeah, you kind of answered this already, but so how is going from you said you moved to GE? How was that like transition for you, and how would you compare statistics and data scientists to someone who doesn't? How would you explain the difference between the two?
Okay, so I'm a statistician and a data scientist. So, data science, I think, is broader than statistics. In terms of the transition to GE, the way that happened was I have a LinkedIn profile, and I heard from one of their recruiters one day, and they said they thought I was a really great fit for this principal data scientist position. And then they sent me the job description, so they're posting me for it. And I have to tell you, if I had just read this posting, I would never have applied for the job. It was machine learning this and artificial intelligence that, and I think they had machine intelligence in there for certain parts of it. And it wasn't until I got to the very bottom, which was about what are the qualifications for someone they want for this job, that they even had anything about, by the way, a PhD in statistics is a great qualification for this. So that was very interesting, because I didn't think of myself as a data scientist. I was like, I'm a statistician. I'm a hardcore statistician. I don't do this neural network stuff. So that's how that happened. And then I started talking with them, and it turned out that I was a really good fit for their data science group, in the sense that, for example, they had an electrical engineer. So a guy, PhD in electrical engineering, knows a ton about signal processing. They had a guy who'd sort of come out of the financial modeling community. They have a lot of people who are aerospace engineers who've gone back and learned some statistics and machine learning. And they hired me because they wanted somebody with deep theoretical knowledge of mathematical modeling. that's my role, which is something that you will really, really get out of a statistics degree program. In terms of what's the difference between statistics and data science, obviously I think statistics is a piece of data science. What I've learned sort of looking at the community out here is that data science is so huge that there's no one who's an expert in everything called data science. So for example, there are people who are called data scientists who their job is to manage massive, massive amounts of data. It's just saying, you know, how do we store it? How do we move it? How do we even work with, you know, petabytes worth of data in a credible way? And so that's sort of hardcore computer science and computer engineering people. These are not people who do any kind of modeling at all. You also get people who are called data scientists who are from the machine learning community. And the line I draw between machine learning and statistics, which isn't a line so much as sort of a wide, fuzzy band, is statistics. If you're doing inference, you pretty much have to be using probability. Most of the tools we use that are not just strictly visualization tools are probability based. That is not true of machine learning. They have more things that are sort of point estimates where you don't have that probabilistic background to give you uncertainty around it. So for example, linear regression or logistic regression lives in both statistics and machine learning. I would say something like a support vector machine, which if you're not familiar with it, it's an interesting way of drawing a separating plane, sometimes a fuzzy separating plane between two or more classes of data. And but it's not probability based. It grew out of computer science. So data science, I would say, started off being more of the computer science playground, because it did have that background in terms of how do we just manipulate massive data, and a background from machine learning, which was, you know, it's how do we do inference, but not quite the way that statisticians do inference. It's now increasingly recognized that statisticians are data scientists too, and that we bring a unique perspective to data science, because statistics is not just about point estimation. It's not just saying this is my best guess. It's about saying this is how good that guess is, which is something we bring to the table that's fairly unique. So yeah, statistics is a subset of data science, but don't get scared off by sort of the breadth of things that fall under the heading of data science. I've never met anybody who does all of them.
Yeah.
You usually get people who are like really deep in one corner of it. And then, you know, if you want all of that, you really do need a team of people, which is what a lot of places are doing these days.
So in terms of being undergraduates and being preparing themselves to go out and be contributors in, you know, data science generally, I think all of us here in the room are kind of convinced of the value of data and that it needs to play a critical role in the learning process and science and everything. So how can they best situate themselves to be impactful in a data science kind of role? And how can they maybe exploit the specific skills they have from their statistics degree as they go out and try to contribute?
So for specifically for data science kind of role, I will reiterate the importance of computing. And again, you don't have to be a CS major. You just have to be comfortable with a few different programming languages, and you will be well ahead of pack of statisticians at least. I mean, I think I came out knowing R, Java, and Perl really well. And frankly, once you learn a few, then somebody says, oh, well, we only work in Python here. And it's like, well, I learned 3. What's another one? You know, let's go look at the for loop syntax again. So if you want a data science role, just be more comfortable than average with computing. I would say that the unique thing that statisticians bring to the table, and this isn't just in data science, this is in all of my work with scientists and engineers throughout both of my jobs. Statisticians think about uncertainty. And we're trained to do it in a way that I haven't really seen any other technical discipline be trained. In statistics, we can have I don't know as a technical answer. I mean, we can quantify that we don't know and why we don't know. And that's enormously valuable. It's really what sets a statistician apart from somebody who just like runs a statistical tool and gets an answer, is that the statistician is the person who understands, hopefully at least, the uncertainty in that answer, and who understands that, you know, there's fuzziness in a lot of these things, and hopefully knows that, you know, you should always give an interval estimate along with your point estimate so that you can figure out if something's really practically significant as well as being statistically significant. It's hard to understand it, or not understand. It's hard to explain, because I basically spent 7 years sort of buried in statistics and surrounded by statisticians, and I started thinking this way, sort of in a probabilistic way because of that, but I didn't notice. And I didn't realize that statistics had changed the way that I approached problems until I got out to the laboratory. And I realized that I was viewing things differently than everybody else in the room. And then I'd go to the other statisticians and be like, nobody else seems to understand it. And they're like, yeah, they don't understand it because they haven't had that training. And so that's one of the things I think is great about the undergraduate program that you guys are in, is that you get sort of a head start on thinking that way, whereas I was straight math as an undergrad. And the other thing I would say about being a good collaborator, don't be afraid to not know things. It's really scary when you take your first job and you're in that first meeting and people are just throwing around jargon that you have never heard before in your life, and they're expecting you to contribute and you have no idea what's going on. It's also really, really normal if you're a collaborative statistician. It is routine for me to walk into a room and you know, I, by definition, am the person who knows the least about that problem. And I have no, you know, background in physics or chemistry or whatever that would sort of give me a leg up to understand. So when you walk into a problem and you walk into a meeting and you don't know what's going on, just ask questions. It's normal, and most people are nice and they understand that, you know, you don't know everything that they know. So don't be afraid to not know things. Don't be afraid to ask questions, and keep in mind that the statistical training that you're getting allows you to bring value. You don't have to be a better physicist than a physicist. You don't have to be a better chemist than a chemist. You are going to bring them insights that they won't get otherwise just by knowing statistics. And I don't know if it becomes a lot easier to believe once you see it a few times, but trust me, the things you are learning are things that other scientists do not know, and they will be, you know, stunned by your ability to do a simple binomial confidence interval. I'm not even joking. You know, you can make a living off of the exact binomial confidence interval and just really understanding it, which boggles the mind when you consider, you know, all the other things we can do.
Okay, what else? Thomas.
I remember I saw that on your website that you are a PhD student. You were a PhD student. So what's the differences between a master's student and an undergraduate, like just a benchmark, and a PhD when they go to work?
So what's the difference between undergraduate statistics major, a master's student, and a PhD student? Big picture question here. What kind of work differences and what kinds of career differences would they see? Not everybody in the room is going to go to graduate school, or at least they don't know it yet, or they maybe don't know that they are going to go yet. But so, you know, they'll be wondering, what are my options, from get a job with an undergraduate degree to keep going to going all the way? Big picture advice. What would you say?
Yeah. So I can't necessarily answer all of that because I've only worked 2 places, and like Lawrence Livermore hired master's level and PhD level statisticians. So I would say if you want to work at a national laboratory, go to grad school. GE does hire bachelor's level people, and the difference in those jobs, it basically has to do with the degree of independence that is expected of you. So I'll start working backwards. If you get a PhD in anything. Essentially what that degree means is that you can independently develop new solutions to problems in that discipline. So basically, if you have a PhD in statistics, there is some expectation that I can hand you a problem that not only have you never seen before, but maybe nobody's ever seen before, and you can eventually, slowly, with lots of fits and starts, figure out what to do. That's the ideal world. It doesn't always work out quite that way. You're also expected to have a lot of background knowledge because, again, 7 years thinking about statistics, that will allow you to solve already solved problems faster. So sort of working back to a master's degree, there's not necessarily the expectation that you can solve a problem nobody's ever solved before. There is an expectation that you have a very solid grounding in your discipline. You may not know everything. I mean, I realize that this may seem like forever away if you're, in particular, if you're just starting your undergraduate career. It's like, oh my gosh, 6 years of training, I'll know everything. No, you won't. When I came out of my master's degree, I was feeling like there's so much I don't know. I don't feel ready. So master's level people are expected to be able to apply best practices in their discipline, potentially with guidance from either senior master's level people or PhD level people who've just seen more stuff. So that was sort of how it worked at the laboratory, where when we hired master's level people, they got more mentoring and sort of more oversight and guidance than the PhD level people. They also had somewhat less independence. It's a trade-off between freedom and I don't know, not freedom and trust. That doesn't sound quite right. But when you're sort of thrown into the deep end, like the PhD level people are, you're also given a lot more flexibility. Whereas at the master's level, you'll have more oversight and more help, but also less flexibility. For bachelor's level, it's sort of ramping up the level of oversight from master's level, because you haven't seen as much stuff. You don't have as much exposure to different techniques. You may not have implemented different techniques. At both of the places I have worked, there is an expectation of constant learning. So, for example, there were plenty of master's level people at the lab who went back and got their PhDs, or even who didn't go back and get their PhDs, but who, after a few years, were viewed as working at that level. So it's the difference you're going to see at the kinds of places where I work. I mean, there are other places where you can have a bachelor's in statistics and data science and just do your whole career there. You're expected to constantly be trying to grow. And so the difference between bachelor's, master's, and PhD is how far have you grown already?
Okay, thank you. What else? One question from me. What's it like being a woman scientist and statistician these days? There was some kind of ranking that came out from U.S. News and World Report recently, and I think they always are ranking things, and they ranked careers by gender, and I think it was number 1 or number 2. Top career for women was statistics. Somehow they, decided that.
It wasn't top for men? What?
I don't know where men
no, it's
was,
the best
but
career.
number 2, yeah, showed up for women. So yeah, what's it like? Just generally being a woman in graduate school and in science and in statistics in particular, if you don't mind.
Oh, I don't mind. I will tell you, I've heard stories from women of an older generation than mine that are very intimidating. The kinds of things they went through and the kinds of challenges and just not nice stuff that they experienced when they were sort of coming in and being the first woman in an environment. And I feel like I've been very fortunate throughout my career that hasn't happened to me. I've never had like a negative experience I've frequently been the only woman in the room. I've never felt that that was an issue. And that's, I mean, I freely admit that, you know, other people's experiences may have been different from mine, but I've never had problems in that way. In terms of why it might be one of the best careers, there's an extreme shortage of people who can do this. You know, just upfront, particularly because there is more data available now than there ever has been before, and there are different kinds of data, and people are really seeing the value of data in all kinds of, you know, business and government and nonprofit applications. They are desperate for people who know what to do with it. And anytime you have a skill that is in exceptionally high demand, you have a lot of flexibility. I will say that. Like, for example, I am at home this morning talking to you, and there were no issues setting that up. I mean, this was scheduled back when I was still at Lawrence Livermore, and I said, hey, do you mind if I take off 2 hours to talk to, you know, students at 8 a.m.? And they're like, nah, go for it. When I got the job at GE, I said, by the way, I've already made this commitment. Is that okay? They're like, yeah, sure. Yeah. I have permissive time off, which basically means if I go to my boss and say, you know, do you care if I come in tomorrow? And he says, no, I don't have to come in tomorrow. And it's not tracked. So it's not a situation where I have a time bank. I can work from home if I want to. All the places I've worked have been very understanding about work-life balance. By the way, I will say this about Silicon Valley. If you're going to work in Silicon Valley, understand that if you're at a company with really high turnover, if they expect they only get to keep you for 2 or 3 years, they will work you really, really hard those 2 or 3 years. The companies where I've chosen to work, people stay there a lot longer, you know, more than 10 years in many cases. So they're about pacing themselves and saying, you know, we don't want to have to replace you. We want you to you know, work hard when you need to work hard, but the rest of the time you have a life. You know, it's make sure you get enough sleep. Don't work 7 days a week. Don't go crazy with it. And, you know, I'd love to think that that's just because everyone is super nice and I only work for wonderful people, but I recognize that a big part of that is because there's a shortage. They have to be people. They have to be nice to people with this skill set, because otherwise they won't get any. And I suspect that's why it's a really, really nice career to have right now. And by the way, 100%, it is a wonderful career to have right now. And I mean, out here in California, unless you want to buy a house, that's hard in California. There's a lot of great stuff about being a statistician or data scientist.
Cool. All right. Any other questions? Emma, go ahead.
So, from what you said, the National Laboratory seems to mostly work in like the hard sciences, like with physics and biology and such. Do you know where people go if they're statisticians and they want to work in like more social sciences, philosophy, sociology?
Do you have any input or perspective on statisticians who maybe go in a different direction, instead of biology, chemistry, physics, engineering, sciences, maybe social sciences, education, things like that? Yeah.
Do I have any insight? I've never done it. I know a lot of people who've done it. And I know that in particular in government, there are a lot of statisticians. It was never that appealing to me. I love science. I went to a math and science magnet high school. I was in robotics club. I'm just a hardcore science nerd. Mm-hmm. And so a big part of big reason my career has been the way it's been is because I figured out what I liked and I went for it. So the reason why I love my jobs is because they push all those buttons for me. They push the science buttons and the engineering buttons and the math buttons, and it's all really great. If what motivates you is different from that, one of the nice things about statistics is you can structure your career in that way. So for example, I'm trying to remember what it's called. There's Statisticians Without Borders. There are a bunch of groups that try to like connect statisticians with sort of social science needs for governments to try and help them crunch their data. There's a lot of work in government. There's a lot of work, in academia, applying statistics to other kinds of problems. If that is what excites you, then do it.
Yeah.
100% do it. I received some very good advice when I was in high school that you should not pick your job based on how much money you make, because if you hate your job, they can't pay you enough to do it. So you want something that's intrinsically rewarding. And for me, that's science and engineering. If for you that's something else, statistics will let you do that, which is really very cool.
Okay. Thomas?
So you first worked in a laboratory. I'm just curious about how did you make a decision among all the career options? Like, because there's a lot of career options for a stats major. Like, how did you figure out, like, what did you want to do?
How did you figure out, your particular path? So you've talked about that some, but coming from a perspective of there's lots of job directions that we could go from, undergraduates, lots of options. How did you wind up in your particular path? Not the historical lesson again, but maybe just some advice on how does one wind up in one particular path?
So I'm a 5-year plan kind of person. I always have a 5-year plan, and I have never once actually made it the full 5 years into the plan. I remember being an undergraduate and what I thought I was going to be when I grew up at that time. And frankly, I thought I was going to be a veterinarian because, like science, like animals, let's go ahead and do that. That ended up not happening because of for example, because of the financial crisis in like the 2000, 2001 timeframe, where all of a sudden that became a lot more expensive than I'd anticipated. And I said, okay, well, I need to do something I like to do that would let me make money. What makes me happy and is more achievable financially than the veterinary medicine. And I give that example, not saying that people shouldn't be vets and they should go into math, but by saying you should be flexible and you should be open to the opportunities that you see. A lot of things that happened in my career were not planned. I won't say they exactly happened by accident, but it was certainly not something I anticipated. Working in GE Aviation, not something I anticipated. Working at Lawrence Livermore was not something I anticipated. Getting a doctorate was not something I anticipated. It was a situation where I looked at my life and what I was doing and what I wanted. And I said, okay, well, the situation's changed. I've learned something. So, I need to sort of change course and do something different. The reason I ended up getting a PhD was because I looked around at kind of the master's level jobs that I saw, and I didn't really want one. And I had also just passed the qualifying exams, and I knew that I was never going to put myself through that again in my life. If you don't know what qualifying exams are, ask Dr. Dabney. They're an interesting ordeal. And so I said, you know what? I want the kind of opportunities that people with PhDs have. And I've just, achieved this I've jumped this hurdle that would allow me to get a PhD at Texas A&M. Let's just go for it. And then I was going to be an academic. I was going to write papers and teach my whole life. And then I met this guy from Lawrence Livermore National Laboratory who basically convinced me that no, that's not what I wanted to do. It's what I loved was science and engineering research. Wouldn't it be great if I could just do that all the time? And yeah, it really was great. In terms of the consulting service, that came out of me basically complaining at every staff meeting we had for 2 years that we had no way to sort of support people in statistics and sort of get them an introduction to what we could do for them. And finally, my boss came to me and essentially said, put up or shut up. Here's the money. You go run it. And I did. So it comes of not being afraid to take risks, of not being afraid. Well, maybe you are afraid, but you do it anyway. Of not refusing to pivot when you learn something about yourself or about an opportunity or whatever. And it's about knowing what makes you happy, which that's still a work in progress, is understanding what makes me happy. But I figured out a long time ago that, I really, really, really like working with scientists and engineers. You know, like I've talked to people at other organizations, sort of in Silicon Valley, and I would miss that. So that was a choice I made a while ago, which is, you know, I could go someplace else. I could maybe make more money. I could be part of, you know, the trendy Silicon Valley thing, but I would really miss the science and engineering aspects of what I do. So I'm not going to do that. And that's going to be different for each of you. And I will also say that when I was where you are now, I did not understand what I wanted out of life as well as I do now. It's something you learn. You try something new and you find out you really like it. Or you try something new and you find out that something that you thought you would like, you know, isn't actually that appealing. So just, you know, take life as it comes. And there is no harm in changing your mind and saying, you know, well, I was going to be a vet, but, you know, this other opportunity looks really good. There's nothing wrong with changing the plan.
Cool. Thanks. All right. Trip, go ahead.
You talked a lot about what you were doing at Lawrence Livermore with you know, physics and chemistry and things like that. I was just curious if you could expand on how exactly statisticians can help those kind of professions.
Sure. I actually heard that one. The answer ties back to what I said before, which is that, pardon me a second. You get training as a statistician and a style of thinking as a statistician that's very, very different from what you get as for example, a physicist. So like I'm friends with physicists, and so I asked one guy, you know, what training did you get in setting up an experiment to figure out, you know, how many measurements you need to take? And he said, this is physics, we only need one measurement. And it's stuff like that. I can give you a lot of very amusing physicist stories if you've got the time. There's just a different philosophy in those disciplines, and they study different things. I mean, they're studying how physics works. They are not studying how to model data. So for example, when I say people are like stronger mathematically than me, that means they took, you know, went way deeper in things like partial differential equations. They didn't study probability like I did. I walk in there, I know probability cold, and they don't. So for example, what we did with the neutron detection project, which is, it's the one where I probably worked the most extensively with physicists. I wish I could show you a picture, but basically what they do is that there's this way of measuring two properties of a particle when it hits a detector.
Do you happen to have do you happen to have a electronic file or something? Because it
not on my phone. No,
oh, okay.
Sadly I don't. But basically what you get is sort of these two lobes where there's like one coming out like this and then another one coming out like that. And the physicists, you know, being relatively smart people, said, let's draw a line in between them. And if it's above the line, it's a neutron. If it's below the line, it's a gamma ray. And that's, you know, that's not a horrible thing to do. But then they said, how do we measure the accuracy of our classifier? Because it is a classification problem where they want to figure out which are the neutrons and which are the gammas so they can kick all the gammas out. And when you read the literature of what they did, it's not actually that hard a problem. There are a lot of different ways to do it if you're a statistician, if you're trained to think in terms of probabilities, in terms of distributions of things, where you can look at like probability of misclassification, you can look at like likelihood ratios for a distribution of neutrons and a distribution of gammas. And they were doing this really weird thing where like you'd fit a normal distribution to the top one and a normal distribution to the bottom one at a slice, and then you would take the difference of the means and you would divide by the sum of the standard deviations, which I hope everyone in that room just flinched when I said the sum of the standard deviations. But they don't know. I mean, they're not trained to think that way. So it's not that you're working with people who aren't smart. And that was like a huge revelation for me, was that there are people who are really, really, really smart who have no idea how statistics works, like none. And it's not that they can't understand it, it's just that they spent all of their time, you know, studying nuclear physics, which is a non-trivial discipline that I don't understand very well at all. So just by coming in and saying, you know, you really shouldn't be adding standard deviations like that, and by the way, here are a bunch of other options, I was able to bring stuff to the table. I worked on another project. It had to do with the National Ignition Facility. And I go through this in detail in one of my talks on YouTube. But basically, they had a situation where they had to prove that a component had this absurd reliability, like, 1 in a billion chance of failure. I don't remember exactly what it was. And if they couldn't prove that, then they couldn't run NIF within sort of its approved tolerances for risk. And of course they couldn't prove that, because it would take, tens of billions of tests. It would be this horrible problem. And they came to me because they'd done this calculation. They'd done it correctly, by the way. And they said, please tell us we've done it wrong and we can do fewer tests. They hadn't done it wrong. But what they had ignored was the fact that there were actually 2 components in the system that would have to fail at the exact same time. They didn't realize that by modeling 2 independent failures, you could basically knock this down to a manageable problem from the problem they couldn't solve. I mean, that was what I was talking about with the binomial confidence interval. That is all that was. It was 2 binomial confidence intervals and the Bonferroni correction for, a multi-billion-dollar engineering project. And again, it's not that I was so much smarter than the other people in the room. I wasn't. It's just that I had seen that idea before. I knew that, you could look at the uncertainty in 2 things at once and 2 independent things at once, and that made a big difference. Mm-hmm. So yeah, it's as part of the consulting service, I saw so many projects, and I can't say that there was ever a project where statistics, just couldn't do anything, unless there was no data, in which case statistics could say, go get some data. But yeah, it was very, very interesting to me to have those experiences and just see the real power of what I learned and what you're learning now, because I didn't expect it, frankly. It was a surprise to me, but it's very real.
Cool. Emma?
You found that it's easier to work with quantum physicists because they work in a world with more probability? Have you ever gotten to work with quantum physicists on problems?
Question, what?
Yeah, I heard it, the quantum physicists.
Yeah.
No, they're harder to work with in many ways. So there's a thing called statistical physics, which isn't statistics though. But so here's something else that's interesting. I know probabilists who are very bad statisticians, and similarly, I've known quantum physicists who are very bad statisticians, and it has to do with, again, it's not math. It's not that they can't hack the math. They absolutely can. I mean, they can work with characteristic functions all day long. It's that they don't have training in sort of experimental design and working with data. This is a completely, it's a separate topic from the mathematical topics, but it's also something that statisticians are trained in that most people aren't. Like I worked on a project with a really great mathematician who just couldn't make the connection between the model we were building and the data that you needed to fit the model. And it was again, it was odd to me because this guy is smarter than me, better at math than me, but he'd never been trained to think about like an experiment as a way to sort of fit a probabilistic model. And the issue that you run into with physicists is they believe their models a lot more than statisticians do. Like I will fit a linear regression model when I think I can get information out of it, even when I know it's the wrong model, even when I know, the errors have non-independent correlation structure, even when I know that the actual problem is nonlinear. You can do something like that and say, I know it's wrong, and I'm not gonna, take it as gospel, but I am using this to get one specific insight to the problem, and I know that particular insight will come out all right. Mm-hmm. That's sort of, I don't want to say model misuse, because it's not like you're doing something that's morally or even technically wrong, but that sort of model fuzziness is something that a lot of other disciplines don't think about, and so they're not as quick to use it. So yeah, it's you can work with people who know probability stone cold and still bring something to the table with statistics.
Mm-hmm. Cool. Any other questions? All right. Well, thank you very much for your time. Let's thank Dr. Lennox.